So Robert asked me to come here and give an introduction to these things that we call the Lambda polytopes. And David asked me on Monday why we call them Lambda polytopes. I don't really have a good answer for that. I think we called them delta first, but then we realized other people use delta for simplices, and our polytopes aren't simplices, so we tried to come up with another letter, and lambda looks kind of like delta. If you have suggestions for better names, maybe we can change it. Let us know. So here's my outline. I'm going to start by giving the backstory, so where these things came from, why we started working on these things. And then I'll go into the definitions and our primary motivations, talking about the lambda polytopes. Then I'll go through some applications of them. Part 3, this is basically an ad. I'm going to try to sell you these polytopes and convince you that they're things worth working on, things worth studying. And then the purpose for part 4, looking at the mathematical structure of the lambda polytopes, is I've heard the complaint a few times that people are convinced that these are interesting things worth studying, but there's already a few papers out. There's a decent amount of work on these things already, and people say it's hard to get started, to get caught up. So I'm going to try to just summarize what we know so far about these polytopes. So part 1, the backstory, the origin story of the polytopes. I have to start by introducing the stabilizer formalism, or maybe I don't. I think we know from David's poll on Monday that this slide is entirely unnecessary. Everyone knows this already, but maybe I'll just introduce the notation anyway. So we're doing quantum computation on qubits, not just qubits. So whenever you see n is the number of qubits, and then d is going to be the qubit Hilbert space dimension. And then most of what we do is geometry in this space, Herm of H. Herm of H is this real vector space of Hermitian operators on the Hilbert space H. And H is going to be usually just the n qubit Hilbert space. So stabilizer formalism consists of 3 things. We have Pauli measurements, Clifford gates, and stabilizer states. So for qubits, it's just the regular Pauli operators, maybe strings of Pauli operators on all the qubits. And we have a suitable generalization of the x and z Pauli operators for qubits. And then when you see pi, subscript p, superscript s, this is going to be a projector corresponding to a Pauli measurement p, giving a measurement outcome s. Okay? Clifford gates are defined by the property that they map Pauli operators to other Pauli operators under conjugation. And I've got this proportional to symbol instead of equals because sometimes there's phases that come up here. And these phases can be a bit tricky to deal with. And with Robert and Gian and Paulina Feldman in Vancouver, we got a whole paper which is largely about the phases that come up here and up here. But that's not the point of this talk. So for our purposes today, I'm mostly going to pretend they don't exist. And then the last thing we have in stabilizer formalism is stabilizer states. And these are just joint eigenstates of the Pauli operators. So the computational model we're looking at is quantum computation with magic states. This is my picture of what it looks like. You got a bunch of magic input quantum states. They get fed into some quantum circuit, which consists of just Clifford gates and Pauli measurements. And then you get some computational output, which is derived from the measurement outcomes, the outcomes of these Pauli measurements in the circuit. So we know that, everyone knows here, that circuit model with the Clifford plus T gate set is universal for quantum computation. But here we're restricting the gates. We only allow Clifford gates, no T's. And so, yeah, Cliffords by themselves, they're not universal. In this model, we're not allowing any extra gates. We restore universality by allowing the injection of magic states. That's these magic states I've included at the start here. So here's an example of it, standard example. If you include this particular magic state, then using just Clifford operations and Pauli measurements, you can effectively implement a T gate on this other state. So stabilizer operations in Clifford gates and Pauli measurements supplemented with these non-stabilizer input states. This is also a universal model of quantum computation. The big question we want to approach is which states are magic, by which I mean which states, when you add them to Clifford gates and Pauli measurements, give you something computationally interesting. We know that you can't include just any states and get something interesting, because we have examples like this Gottesman-Mill theorem that says if all you have access to is stabilizer states and Clifford gates and Pauli measurements, then that can be efficiently simulated by a classical computer. So you need something else. You need something that's not a stabilizer state. And the question is, which states give you something useful or interesting? So that's what I'm going to mean by, different people use this word differently, magic states. I'm just going to, when I use the word magic state, I just mean any state that when you add it to this set of operations, you get something computationally interesting. Now there's a way of approaching this question that proceeds by seeing what you can simulate efficiently classically. So trying to extend the Gauss-Mendel theorem by adding efficient classical simulations for other possible input states. And there's a framework for defining these classical simulation algorithms based on these things that we call quasi-probability representations. So I'll go through the abstract definition first of what I mean by a quasi-probability representation, and then I'll try to give a more geometric intuition for what's actually happening here. So this is the abstract version of it. You start by defining a set of Hermitian operators we call A sub alpha, and here V is just an index set for these operators. There's a finite set, and we need them to satisfy these four properties. So first, on the next slide, I'll say why we impose these things, but first I'll just go through the properties. We need them to span this space of Hermitian operators on the Hilbert space. We want everything to be normalized, to have trace 1. This is how you get quasi-probabilities out. And then for representing the dynamics of the computation, being Clifford gates and Pauli measurements, we want these nice properties with respect to Clifford gates. So if you conjugate one of these operators by a Clifford operation, you get another one of these operators back again. And for Pauli measurements, it's a little bit more complicated. Suppose you do a Pauli measurement P and you get measurement outcome S. That's identified with a projector. So if you apply this projection to one of these operators, you get a convex mixture of these operators. Now, this is the abstract way of how we define a quasi-probability representation. Here's what it gives you. This is what the representation looks like. So we call it a quasi-probability representation for QCM, for quantum computation with magic states, because it gives you a way of representing each of the three pieces in this computational model. So we have a representation for states, for Clifford gates, and for Pauli measurements. So here's what the representation of states looks like. Since we have these first two properties, so they span their space of Hermitian operators and they're normalized, any state represented as a density matrix can be expanded in these operators. And then if you take a trace of this equation, you can see on the left-hand side you just get 1, and then on the right-hand side you get a sum of the coefficients. You can say these coefficients are sort of normalized. That's why we call this a quasi-probability distribution, or quasi-probability function. But they're not necessarily non-negative, so it's not a proper probability distribution. And then the other two properties give us these nice update rules under Clifford gates and Pauli measurements. So we have a deterministic update for Clifford gates, and we have this probabilistic update given by this convex mixture for Pauli measurements. So whenever you have a quasi-probability representation with these properties, you get a classical simulation algorithm for quantum computation with magic states. I'll just take you through what that looks like. So remember that this is the computational model. You start with some input state, not necessarily a stabilizer state. You apply a circuit consisting of Clifford gates and Pauli measurements, and you get some measurement outcomes. So we want to simulate circuits that look something like this. In the case where the coefficients in this expansion here are all non-negative, then this really is just a probability distribution over these Hermitian operators. Basically, everything here is just probability distributions over these operators. And so we do the natural thing, just sample operators according to these distributions. So here's what the simulation algorithm looks like. If your coefficients are all non-negative, you sample one of these operators according to this distribution, and then you just propagate this operator through the circuit. And whenever you come to a Clifford gate, you have this deterministic update rule. And whenever you come to a Pauli measurement, you need two things. So first you sample these two things according to this other distribution, which was defined by this property here, this convex decomposition. You get two things, beta and S. S is the outcome of the measurement. So you return that as a measurement outcome, and then you have this update of the state. And so you go through the whole circuit, you perform these updates, and you return measurement outcomes as you go. And that gives you samples from the measurement outcomes, which are distributed according to the same distribution you'd predict using quantum mechanics. But this only works when the representation of the input state is non-negative. In the case when that's not true, so there's some negative values in the representation of the input state, you can still do a classical simulation. It looks a bit different. And in that case, the cost of the classical simulation scales with the one norm of these coefficients, which is something like a measure of the amount of negativity, the amount of negative values that come up in the representation of the input state. So if you add some extra assumptions, so if you assume that these update rules can be efficiently computed classically, and you assume that you can efficiently obtain these samples, then this whole simulation algorithm is efficient for a classical computer. And so this gives you a nice characterization of which states could be useful. If everything is non-negative, then you get an efficient classical simulation for these computations. And in the case when everything is not non-negative, the cost of classical simulation scales with the amount of negativity. Now, this is pretty abstract so far, so it might be helpful to go through some examples. Here's an example, stabilizer quasi-mixtures. In this case, we take the set of Hermitian operators that define the quasi-probability representation to be these things, projectors onto stabilizer states. Okay? So these have all the properties that I went through a couple slides ago. So you can represent any density matrix, any n-qubit operator as a quasi-mixture of these projectors onto stabilizer states, where these coefficients here are not necessarily non-negative, but they add up to 1. So this is a quasi-probability function. And then standard stabilizer formalism stuff. If you apply a Clifford gate to a stabilizer state, you get another stabilizer state. And if you do a Pauli measurement, we know how that works. You get this probabilistic thing, depending on whether the Pauli operator you're measuring is in the stabilizer group of the stabilizer state. And so this gives us a classical simulation algorithm for quantum computations that applies to let's see. This quasi-probability function is non-negative whenever your state is a convex mixture of stabilizer states, or whenever your state is contained inside the convex hull of this set of stabilizer states. So this goes a little bit beyond Gauss-Minnel. Gauss-Minnel is usually just for pure states. This tells us it works for mixtures of stabilizer states as well. But you can do a bit better than this. So this is another example of a quasi-probability representation called the Wigner function. Here we have a different definition for these operators. It looks like this. So you start by defining A0, which is just a sum over Pauli operators. There's some trickiness with the phases, but again, I'm pretending that trickiness doesn't exist for now. And then you get a bunch of other operators by conjugating this first one by Pauli operators. So this also gives you a set of Hermitian operators that define a quasi-probability representation. And so we have the same representation for states. For Clifford gates, we have this deterministic update rule. And same thing for Pauli measurements, we have a probabilistic update rule. These updates are efficiently computable classically. I'm not going to go through the details, but you can trust me on this. Yeah, so this is another quasi-probability representation that gives you a classical simulation algorithm for these kinds of quantum computations. And this does better than stabilizer quasi-mixtures because we have this theorem from David. It says a pure state has a non-negative Wigner function if and only if it's a stabilizer state. But if you look at mixed states, there exist mixed states with non-negative Wigner functions which are not mixtures of stabilizer states. So using this one, you can efficiently classically simulate more than just mixtures of stabilizer states. You can simulate anything with a non-negative Wigner function, strictly more. But there's a caveat here, which is that I wrote it in small letters up here. It only works for odd dimensions, odd-dimensional qubits. Doesn't work for even dimensions. So a lot of our motivation came from taking this very nice result and trying to extend it to even dimensions, trying to extend it to other settings. And it's not just us. A whole bunch of people have tried to do this over the last decade or two. But this was a big motivation, was taking this result and trying to extend it to other settings. Now, I promised a more geometric intuition for what's happening here rather than just this abstract picture. Here's an example of what the simulation algorithm looks like for the case of stabilizer quasi-mixtures. So maybe I'm getting a bit too ambitious with my drawing. I tried really hard to draw an octahedron here. This is supposed to be the set of single qubit stabilizer states. So you got a 0 state, 1 state, plus state, so on. The vertices are stabilizer states. You have the input state of your quantum circuit. You represent it as an affine combination of the vertices of the stabilizer polytope. You can do this with non-negative coefficients if and only if your state is inside the convex hull, so inside this stabilizer polytope. If your state is outside the polytope, then you need some negative values in your representation of your state. So this is a more geometric picture of the same phenomenon I was talking about. And then you have a geometric picture for the simulation step as well, the updates. For Clifford gates, you're just hopping between vertices of this polytope. So here's an example. H just maps 0 to plus. You're just hopping around vertices of the polytope deterministically. For measurements, it's similar, except you have probabilistic updates. Maybe you have to flip coins as you go, and that tells you where to hop. But the whole simulation is just, you start by decomposing your state as a mixture of the vertices. You sample vertices according to that distribution, and then the simulation is all just hopping around the vertices of these polytopes. Maybe I should stop. Does this make sense? No questions so far? Okay. Now, we can try to think more abstractly. If we have this geometric picture, we can think more abstractly about what properties do you need in a polytope in order to get a useful classical simulation algorithm like this. So I'm not claiming that this list is complete, but these are just some things that you might want to have. So first, I'm suggestively calling this polytope Lambda. We'll get to that in a minute. If you have a polytope, you want it to be useful for classical simulation. First thing you need to do is make sure it lives in the right space. So it's a subset of this space of Hermitian operators. So the space where density operators and observables live. You want to make sure everything's normalized to have trace 1. So this is how you get quasi-probabilities out, rather than just arbitrary real numbers. You want to make sure it's closed under Clifford gates. So if you conjugate by a Clifford gate, you map back inside the polytope. This is somewhat weaker than what we usually get. Usually the Clifford group is a symmetry group of the polytope. But this is all you really need. And then you want nice behavior with respect to Pauli measurements. So first you want your simulation algorithm to predict non-negative probabilities for Pauli measurements, which means these trace inner products with Pauli projectors and elements inside the polytope should always be non-negative. This is what we interpret as the probabilities. And then if you perform a Pauli measurement, and an outcome can occur, meaning that these probabilities are strictly positive, then the post-measurement state should be inside the polytope. So if you do a Pauli measurement on any element of the polytope, it should map back inside the polytope. So this is kind of the bare minimum of what you need in a polytope for it to be useful for classical simulation. So now a question you can try to ask is, what's the biggest polytope you can get consistent with these 3 properties? Because I said before that this Monte Carlo style classical simulation applies whenever your input state of the quantum circuit is inside the polytope. So the bigger you make the polytope, the more states you can simulate classically. So we want to ask, how big can you make this polytope while preserving these properties? And we found an answer to that question. It's these things that we call Lambda polytopes. And again, let us know if you have a better name. Here's the definition. Again, we're going to stick with this geometric picture, and then I'll go through the algebraic properties a bit later. This is the definition. So it's a subset of the space of Hermitian operators. Everything is normalized to have trace 1, and then you have to satisfy a bunch of these inequalities. There's going to be one of these inequalities for each stabilizer state. These have an interpretation. This is something, you interpret X as your states. They don't have to be proper states. They don't have to be positive. It's like a generalization of states. And this is saying, if you do some sequence of Pauli measurements, you should expect to get non-negative probabilities. So that's all we're imposing. And it turns out everything just works. So here's what it looks like geometrically. Here, the black part is supposed to be a cartoon of your space of physical quantum states. And then you have a finite set of pure stabilizer states, and you have an inequality for each of these pure stabilizer states. And the inequality says everything in the polytope is to the right of this line. In general, it's a half space. And so you get one of these inequalities for each stabilizer state. You end up taking the intersection of a bunch of half spaces. The result is a polytope, bounded polytope with a finite number of vertices. And so this is what it looks like. So you can think of this, there's a polytope theoretical way of thinking about this. These are stabilizer states. The convex hull of those will be the stabilizer polytope. This is something called the polar dual of the stabilizer polytope. That's another way of thinking about this. And this polytope has all the properties we want for a classical simulation algorithm. So first, it has a finite number of extreme points, vertices. We're going to call the vertices A alpha. So this is what we're going to take to define the quasi-probability representation that we get out of this polytope. And then it has the required properties of updates under Clifford gates and closure under Pauli measurements and all the rest. The difference between this and all the previous quasi-probability representations that came from these polytopes is this one contains all n-qubit quantum states. So this contains all quantum states. This means if we look at the quasi-probability representation we get, there's no negativity anywhere. I mean, it looks roughly the same as all the previous quasi-probability representations. The only difference is every state is inside the polytope, so every state can be expanded in the vertices of the polytope with non-negative coefficients. So every state can be represented as a probability distribution over the vertices of the polytope. Yep. I'll come to that a bit later. I'll come to that a bit later. So this is states, and then updates in their Clifford Gates and Pally measurements look roughly the same as before. But the big point here is no negativity anywhere. So it's not really a quasi-probability representation. It's just a probabilistic representation of universal quantum computation. Here's the geometric picture of what the simulation looks like. It's a bit messy. We'll take it in one piece at a time. So starting with states, you have a polytope. Your state, your input state of the quantum circuit is going to be some point inside the polytope. You start by representing that as a convex mixture of the vertices of the polytope, which you can do. And then for simulation purposes, we're going to reinterpret this convex decomposition as a probabilistic mixture of the vertices of the polytope. And then same as before, Clifford Gates, you're sort of just hopping between vertices of the polytope. And the Pally measurement, same thing. You're hopping between vertices of the polytope, but in a probabilistic way rather than a deterministic way. So this is the geometric picture of lambda polytopes. I'm going to spend a few slides talking about the applications. This is where I'm trying to sell you on these things being interesting things to look at, and then I'll come back to your question after that. So first application is these efficient subpolytope models. Maybe I should have mentioned this before. Previously, for some of the previous quasi-probability representations, you can also show that the updates under Clifford Gates and Pally measurements are computationally efficient for a classical computer. And so that's where you get this equivalence between non-negativity and efficient classical simulation. We don't have that for this model. So although we know these updates exist, we don't have a guarantee that they're efficiently computable in a classical computer. So the simulation model you get out of the simulation algorithm you get out of this, it can simulate any quantum computation, but we're not claiming that it can efficiently simulate any quantum computation. Yeah, we can simulate any quantum computation consisting of Clifford Gates and Pally measurements on any input state. We're not claiming that the simulation is efficient in general, and we expect it's probably not efficient in general. But there's some special cases where the simulation algorithm is efficient. So for example, in odd dimensions, we know that the phase-space point operators of the Wigner function are vertices of this polytope. So if your state happens to be inside the convex hull of just those vertices, then you get the Wigner function simulation back again. And you can generalize this idea. Whenever the support of the distribution representing your input state is restricted to a subset of vertices for which these updates under Cliffords and Pallys is computationally efficient, then the whole simulation can be computationally efficient. And so this gives us a path forward. You can expand the scope of what you can efficiently simulate classically by characterizing more vertices of the polytope. So that's our goal now, is characterize more vertices of these lambda polytopes. And we've made some progress in this direction. Here's an example. I'll take you through the definition, but the result is going to be a small family of vertices for any number of qubits. So we're going to look at sets of Pally operators, omega, satisfying these three properties. So first is like a closure condition. If you have two operators in the set and they commute, then the product also has to be in the set. Second property is there exists a non-contextual value assignment function for this set of Pally operators. This talk isn't going to be about contextuality, so I'm not going to say what this means. It's just a function satisfying certain consistency conditions. So there exists one of these functions. And then third property is that omega is inclusion maximal subject to the first two constraints. So if you have a set of Pally operators satisfying these three conditions, then you can write down this operator here, which is just a sum over the Pally operators in the set, weighted by this non-contextual value assignment function. This operator is a vertex of lambda. And for operators of this form, the updates under Clifford Gates and Pally measurements can be computed classically, efficiently. So same thing as before. For the odd dimensional case, if your probability function representing your input state is restricted to just operators of this form, then the whole simulation is efficient. So this is one example of a family of vertices for which simulation is efficient, but this is a fairly small subset of the vertices. These can be classified. We have a characterization of exactly what these operators look like. They have this kind of structure. So any one of the, maybe I should say, we call these operators C and C operators. C and C is for closed and non-contextual, because this first property is something like a closure under this restricted product, and then second property is non-contextuality. So CNC is for closed and non-contextual. So any CNC operator looks like this. It has a structure where you got three pieces. You have a stabilizer state tensor factor, projector onto a stabilizer state. You have this core part of the CNC operator, and then you mix things up by conjugating by a Clifford gate, Clifford operation. So the interesting part, the non-stabilizer part, is this core, which looks like this. It has the same structure as I had on the last slide, where you just sum over some subset of Pauli operators, weighted by a non-contextual value assignment. But we can say exactly what the commutativity structure of these Pauli operators is. Basically, they all pairwise anti-commute, and you can choose these signs freely. So the number of terms that appear here is linear in n, and then the other part is stabilizer stuff. Now, this is kind of interesting. These anti-commutation relations look the same as, I don't know, it came up before. What are these anti-commutation relations? Fermion operators, yeah. These are the anti-commutation relations of Majorana and fermion operators. And we didn't really know why that was happening, why these things come up here. We still don't really know. So if you know, then maybe you can tell us. But we tried to generalize this. So here we have operators that look like linear combinations of Majorana fermion operators. Maybe the next thing we can do is try looking at quadratic polynomials of Majorana fermion operators. That's what we tried next. It relies on these generalizations of these Jordan-Wigner transformations. So let's explain what this means. Any n-qubit Hamiltonian can be expanded in Pauli operators. The Pauli operators are a basis. There's this theorem from Adrian Chapman and Steve Flamia that says when a Hamiltonian expanded in the Pauli basis has one of these Jordan-Wigner style transformations, mapping to free fermions. So their theorem says you look at the anti-commutativity graph of the support of the Hamiltonian, so the Pauli operators that appear in this expansion. If this anti-commutativity graph is a line graph, then there exists one of these Jordan-Wigner style transformations, or mapping to free fermions. So here's what that looks like. Here's an example of a set of Pauli operators that might appear in some Hamiltonian. These are just two qubit Pauli operators. This is the line graph of this graph over here. So what a line graph means is for each edge in this graph, this is called the root graph. For each edge here, you have a vertex over here, and you have edges connecting vertices if two edges on this side share a vertex. So XX shares a vertex with Z1, and so you have an edge between XX and Z1 on this side. So this is a line graph of this root graph. So there exists one of these Jordan-Wigner style transformations. The way you get it is you identify each vertex of the root graph with a Majorana fermion operator, and then you identify the Pauli operators, which live on the edges, with products of the two vertices on either side. So this tells you how to map Hamiltonians to free fermion models. Now, our motivation is a little bit different. We want to construct a new quasi-probability representation based on this idea. So we call these things line graph operators. We construct them by the following procedure. So first, we choose a set of Pauli operators, omega, such that the anti-commutativity graph is a line graph, such that there exists one of these Jordan-Wigner style transformations. We then project the lambda polytope onto the span of the operators that appear in this set. The result is another polytope. So you're projecting a polytope, you get another polytope. You choose a vertex of that new polytope, the projected one, and then lift back to the original space. And then you choose a stabilizer state in the Clifford gate, and you return something with a structure. So similar structure as before, but now this is the line graph operator instead of a CNC operator. And for a certain subset of operators that can be constructed by this procedure, you get more vertices of lambda polytopes. So here's another theorem. It says for any set of 2n plus 1 pairwise anti-commuting Paulis, so these are like the Majorana fermion operators, there exists a choice of signs labeled by this function eta, such that this operator, you can write down, is a vertex of lambda. And maybe it's a bit obscured here because I've got products of pairs of operators here. But if you expand this in the Pauli basis normally, then the operators that appear here, this is the anti-commutativity graph of these operators is the line graph of a complete graph. So it fits in this framework. So this is another family of operators. Updates under Clifford gates and Pauli measurements on these is also computationally efficient. And so it gives you more, another classical simulation algorithm that can simulate even more states. So this is the goal. We're going to try to expand the scope of efficient classical simulation by characterizing more vertices. But this is basically all we have so far. We're still working on this. I'm running out of time, so maybe I'll go over this quickly. I just want to mention a couple of other applications briefly. I'm not going to go into complete detail. This is from a paper a while ago. Ben Reichart was looking at distillation of multi-qubit states. And he has this result where he looks at states that lie directly above a facet of the stabilizer polytope. And he says, by bipolar duality, if you look at states that are above a facet, you can equivalently see this as a noisy version of a vertex of the lambda polytope. So you take a vertex, you add some noise. If you have enough noise, meaning your state is close enough to the facet, then he shows that every n-to-1 stabilizer reduction, so any map that consists of clever gates and Pauli measurements and tracing out subsystems, things like that, which map an n-qubit state to a single qubit state, will map n copies of your state inside the stabilizer polytope. And the reason he wanted to do this is we're talking about magic state distillation. He was also looking at the problem of which states outside the polytope, the stabilizer polytope, could be useful for magic states, for magic state distillation. And he wanted to see if the question of universality for multi-qubit states reduces to the problem of universality for single qubit states. So if it were the case that being outside the stabilizer polytope for multi-qubit states can always be mapped by a stabilizer reduction to a single qubit state outside the stabilizer polytope, then the question for multi-qubits reduces to the question for single qubits. But because he has this result, that's not true. So you sort of have to treat the multi-qubit case separately from the single qubit case. It's more like a no-go result than result, but it's another application of these polytopes, because he looks at these. He didn't call them noisy vertices of the lambda polytope. He was just talking about the stabilizer polytope, but you can see it as another application. One more application is hybrid quantum classical computation. So the idea here is you have some quantum computation that requires some number of magic states, but maybe your quantum computer is small, you don't have access to that many magic states, so you want to offload some of the computation to a classical computer. So you start with some quantum computation you want to do, but you don't have access to enough magic states, you map that to a smaller quantum computation, supplemented with some classical side processing. And there's a standard way of doing this from this Bravius, Smith, and Smolin paper, where you start by decomposing your initial magic state as a mixture of things that look like this. So you still have n minus m magic states, and then the rest is a decomposition in stabilizer states. And then it looks more or less the same as one of these quasi-probability-based classical simulations, where you're only simulating the part of the input state that you decompose in stabilizer states. So you sample something that looks like this, a state that looks like this, according to this distribution. Maybe I should say this typically isn't non-negative, so you need a modification of this to get a proper probability distribution. But you sample states that look like this according to some probability distribution, and then you use standard stabilizer techniques to reduce the computation on this product of a stabilizer state with a magic state to a computation on just the magic part. And that's the classical side processing, is the reduction of a computation on this thing to a computation on just this part. And the cost scales, again, with the one norm of the coefficients that appear here to measure the amount of negativity. But now, we know that there are better quasi-probability simulators than these decompositions in stabilizer states. So the question you can naturally ask is, can you use one of these other quasi-probability simulators in place of the stabilizer quasi-mixtures? And the answer is not so clear. It's a bit tricky. And the reason is, you can try doing the same thing. Start by decomposing your initial magic state as a quasi-mixture of things that now look like one of these Hermitian operators, or these generalized phase space point operators, tensor product with fewer magic states, and you see what happens. You sample one of these things according to your distribution. The problem is that these samples that you obtain typically are not contained in Lambda, which means if you were to try to do this, basically these stabilizer reductions that map to this smaller problem on just the magic part can't be done, because you're sort of predicting negative probabilities for your Pauli measurements, and that's not good. So here's another. The point is, this is another application, is a no-go theorem for extended hybrid quantum classical computation methods. Now, part 4 is the mathematical structure. I'm just going to try to summarize what we know already about these polytopes. And it's not going to take that long because we don't actually know all that much. This is why we're trying to sell these polytopes is we think there's interesting structure here, but it seems like a hard mathematical problem. So I'll tell you what we know, and then maybe you can help us work on this in the future. So your question was about how many vertices are there. This is what we know about the number of vertices. So we've got two cases here. First, d equals 2, so qubits. This is telling you how the size of the polytope scales with the number of qubits. So first, the dimension of the space, the dimension of this space of Hermitian operators is already exponential in the number of qubits, 2 to the 2n minus 1. The number of facets, you have a facet for each stabilizer state, right? So the number of stabilizer states is the number of facets. It scales like 2 to the n squared, pretty big. The number of vertices, we don't know in general, but it seems pretty big. So for a single qubit, the lambda polytope is pretty simple. It's just a cube. But already by the time you get to 2 qubits, you're in a 15-dimensional space, and you got something like 22,000 vertices. You can find these vertices numerically. You can find all of them. But then by the time you get to 3 qubits, you're in a 63-dimensional space, and you can't even do computational stuff. So we tried enumerating vertices. We get a lower bound of 4 trillion or something, but we don't really know how many there actually are. We can't write them all down. And you can find an upper bound for the number of vertices, but it's this crazy double exponential thing. So a lot of vertices is the answer. We don't know how many exactly. You can do the same thing for a single qubit, but scale the dimension. And again, things grow pretty quickly. Number of facets is the number of stabilizer states. I've only got the prime numbers here. It does work for any dimension. It's just things are a little bit simpler for prime dimensions. These formulas here only work for prime dimensions. I think you know exactly how many stabilizer states there are for composite dimensions, right? Yeah. So if you want to know these numbers for composite dimensions, you talk to Tanmay. But we have this new result from last year that says you don't actually need access to all the vertices. You only need a small subset of them. So here's what this result says. First, for universal quantum computation, you don't need arbitrary sequences of Clifford Gates and Pauli measurements. This is what you were going to say, is it?
Yeah.
Okay, good.
Comments deleted.
Okay, you don't need arbitrary sequences of Clifford Gates and Pauli measurements. For universal quantum computation, it suffices to just have an input state that looks like a product of single qubit magic states, and then a sequence of n commuting Pauli measurements on this magic state. You don't need all these other things. And if you're starting from here, the relevant number is not the total number of vertices. It's just the ones you can reach by applying a circuit that looks like this to this fixed magic state. And that number is pretty small. So here's the result. The number of vertices of lambda reachable by applying a circuit that looks like this to a fixed magic state can be specified with 2n squared plus 3n bits. So pretty small compared to the total number of vertices. And it relies on Carre-Theodori's theorem from convex geometry to bound the sizes, the cardinality of the support of all the probability distributions that come up. And then you run through a computation and you just count the memory requirements as you go. And it turns out you need 2n bits to specify the first sample from the first probability distribution. You need 2n bits for each Pauli measurement. You need 1 bit for each measurement outcome, and then another 2n bits for each updated sample as you go. And so you end up with, a linear number of terms, each of which is linear in n, and so the result is quadratic in n. That's the basic idea. So the number of vertices you actually need to simulate quantum computation is pretty small compared to the total number of vertices. Here's the result again. The number of bits you need to specify the vertices is quadratic in n. I think last thing I'll say, this is the project now, is to try to characterize more vertices of these lambda polytopes. We know of a few examples. So for example, for odd dimensional qubits, we know that the phase space point operators of the Wigner function are vertices. For qubits, we have these CNC operators that I talked about. We have some line graph operators that I mentioned. But this is about all we know for vertices of the lambda polytopes. This is a fairly small subset of the total number of vertices. One other mathematical fact that we know about these polytopes, everyone asks me this question whenever I give a talk on these, is how does it behave with respect to tensor products? If you have some operator x in lambda on m qubits, some operator y, lambda on n qubits, if you take a tensor product of the two, then it's not necessarily in lambda on n plus n qubits. So these polytopes are not closed under tensor products. But you get this version of something similar, which is if you have a vertex on lambda m and you have an n qubit stabilizer state, and you take this tensor product, then the result is a vertex of lambda m plus n. So it's not generally closed under tensor products, but you can take tensor products to stabilize your states and stay in lambda. This is also something we know. So to finish, I'll just say this is sort of where we stand now. We know that if you have, this is a picture that Robert drew, if you have a probabilistic representation of quantum computation using the full lambda polytopes, but that computation, that classical simulation algorithm is inefficient in general. But if you look at restricted versions of it that only use a subset of the vertices, like these stabilizers or CNC operators or line graph operators, then this classical simulation is computationally efficient. And so the problem now is to figure out where this boundary between efficient classical simulation and full universal quantum computation is, sort of building up from the ground. This is where we are now, and I'll finish just by pointing you to references if you want to learn more about this.